Module 15, Statistical Power and Choosing the Right Sample Size. Section 1, Statistical Power, Beta and False Discovery Rate. What is statistical power? So in this two-way table, you can see that the highlighted cell, that is actually the second row, the whole row is highlighted here. So basically it is C divided by C plus D. That is what you call the statistical power. It is a fraction of statistically significant results out of all results where the null hypothesis is false. Statistical power, what is that all about? So basically in this two-way table, you can see that the second row, the highlighted row, defines what statistical power all means. It is basically C divided by C plus D is a statistical power, or more formally it's defined as fraction of statistically significant results out of all results where the null hypothesis is false. So null hypothesis false means there is really difference in the group means, for example, and how much is the fraction that the test could able to detect it. That is called the statistical power. So the probability to obtain a statistically significant result assuming a certain effect size in the population is called the power. So the power depends on the sample size, variability, that is standard deviation, choice of the hypothetical effect size. All these controls the power. So you will get a high power when if you use a large sample size or looking for a large effect, or the data with little scatter or variance or standard deviation is very low to get a very high power. There is a very simple analogy that you can see that to understand the concept a bit further. You have a daughter, for example, you ask your daughter, so please go and bring up a tool for me from the attic, or the storeroom. And the daughter goes and after some time just comes back and say, there is nothing there, Papa. So are you going to believe her or not? Well, again it depends on the context, isn't it? So it actually depends upon how big the tool is. Is it like an a snow axe, or is it ice axe, or a big the tool, or is it a very small screwdriver, for example a minute screwdriver for your specs? So had it been a big one, it would have been easier for her to detect naturally, and had it been small one, then she might have missed it by chance. Another factor is that how well organized my storeroom is. If the storeroom had been organized nicely and then she comes back and say there is nothing there, then probably you will trust her, isn't it? At the same time, if your storeroom had been extremely chaotic and the kid come back and says that there is nothing, then probably you will not believe her. That's the same way in the power as well. So, and another factor is how long did she search there? If she spent a considerable number of time in the storeroom and then come back and say there is nothing, then probably you will believe her. But if she instantaneously comes back and say there is nothing, probably you will not believe. So all these are related. The length that the person is spending in the storeroom to search is quite related to the sample size, while how organized, how neatly organized my storeroom is related to the population variance, or the standard deviation or the scatter, and how big the tool is related to the effect size. That is what it says all about. So even after the following, how big the tool is, that is the effect size, a very big tool like an axe, the tool had been really big. Then how original is how organized is the storeroom? So that is what the variability and standard deviation is all about. It's very well organized. And how long did the daughter spend searching in the storeroom? Very long time. So even after all this and come back and say it is not there, then probability is high that you will believe her. So that statement is said to have a high power, because of all these contextual. So basically the power depends upon the context. Now another scenario, so the tool is very small like a forceps, and it's extremely chaotic, and very brief time that the kid has spent then the statement is said to be of the low power. Same way the statistical power is in a simple sense means the power of a statistical test to detect a certain effect size. So how robust or how powerful the statistical test is to diverge minute differences. So that is what statistical power means. So you need an extremely powerful statistical test to detect very slight differences, while you don't need that much power to detect a huge difference. It's already there, the difference is huge, then you don't need that much power. So a test with 80% power could detect slight differences in the group means, while a test with 10% power could detect only very large difference. So that is what the power is all about. So it's something like you can think of like a powerful telescope versus low power telescope. So if the telescope is really high powerful, you can detect even galaxies, right? So I mean extraterrestrial, other than the Milky Way, you can really put the galaxies or nebula, for example Orion Nebula. If you are having a binoculars, then probably you can only see the lunar craters. So that is the difference here, the power of the test. Statistical power is important while deciding how many samples to use in an experiment. So while calculating the sample size, so it is something called power analysis. So that is that's a synonym of calculating the number of samples required to get a certain power. So how much power is sufficient? There is no hard and fast rules, and it's quite ambiguous. So if you want the statistical power, the best one, that is like 100% is the statistical power, then virtually you need a large sample size. So that is the only problem with going with an extreme power of the statistical analysis. If a moderate power is sufficient, then required sample size is also lesser. So usually the power is 80%, kind of common across the disciplines. But again, this is just an arbitrary value, just like the significance level at 0.05. So similarly, the power is like 80% is kind of okay, but again, it really depends upon the context wise. Another related term is called beta. So as you can see, it is also just like the power. It has to do with the second row, not the column, but the row, the second row, the highlighted cells. You can see that 1 minus power is known as beta. So beta is also related to the alpha, which I'm just coming in here. So beta is defined as d divided by c plus d in this diagram. So that is called the beta. So if the null hypothesis is false, what is the probability of incorrectly not rejecting it? That is what beta defines it. So in other words, fraction of false negatives out of all cases where null hypothesis is false. So that is called the beta. So you can compare beta with alpha as well. So beta is quite similar to alpha, the level of significance. So both quantify the chance of making a wrong decision. Error, it quantifies the error. If the null hypothesis is true, alpha is a chance of making wrong decision or false positive. So alpha has to do with the false positive, while on the other hand, the beta has to do with the false negative. If the null hypothesis is false, then beta is the chance of making the wrong decision. That is called false, false negative. So beta has to do with the false negative, while alpha has to do with the false positive. So now coming to another term called false discovery rate or FDR. So what is this FDR all about? The false discovery rate is the expected proportion of type 1 errors. So it has to do with the type 1 errors, or the false positive. I told you 1p positive. So A divided by A plus C is false discovery rate or FDR. It is a fraction of the false positives out of statistically significant results. So out of all results which are statistically significant, how much is the false? So FDR quantifies the false positives in your finding. So FDR is important while interpreting the result is statistically significant or not. So you have to look at the FDR as well. So for example, a drug testing includes that the drug is effective as obtained p-value is lesser than the threshold p-value, that is 0.05. Does that mean that the drug is really effective? Answer is no. It could only be analyzed in context. So it depends upon the context of the study or its prior probability, a concept that we will discuss more when we discuss about the Bayesian probabilistic statistics. So false discovery rate depends upon the context of the study or its prior probability. Let's give one simple example. You know, there are three drugs here, okay, the drug A, B and C. In the case of drug A, you know a little bit about the pharmacokinetics of the drug, how the drug works, little bit only you know. So you don't expect much that the drug might work. So the prior probability you are putting it as 10% is the assumed prior probability. Now let us actually calculate how much would the FDR be in this case. Let us do this work on the whiteboard. So let us now calculate the FDR if the prior probability is 10. So let us write down prior probability is 10. So in this case, so 10% is the prior probability, and how to calculate the FDR in FDR. So as I told you, the false discovery rate depends upon the prior probability or the expectations. So let us write down what is available in the table so that the things gets a lot more clear. So let us say drug is ineffective, that is one option. Another option is that drug works. So let us put that in a tabular format. So drug works. So this option here is that, let's go a little bit further, reject the null hypothesis, reject null, or don't reject null. So well, this is our null hypothesis, right? This is null. Drug is ineffective. So basically this table, this is 2 into 2 table. So here, well, we can also put one more thing, total. Fine. So in this 2 into 2 table, here these are our decisions, while this is the reality. Right. So what is known here is that the prior probability is 10%. So let us say out of 1000 patients, so 1000 is the total number of people where we tried this drug is 1000. So as the prior probability is only 10%, so 10% of the 10,000 would be the people where the drug works, while the rest the drug is not working. So what is the 10% of 1000? 10% of 1000 is simple, it is 100. So it is 100% this drug works, while the rest is 900. So 900% the drug do not work. So that is what the prior probability of 10% means. So out of 100, so as you know, this row is also defined by something called power, statistical power. So we write here power. So this power is defined in this row, while this row is our significance level or alpha. So this row is concerned with the significance level, while this row is concerned with the power. So we also know the power is 80%, power, while sigma is 0.05. So out of 100, because the power is 80%, so out 80% of this total is expected to be a significant result. So the reject the null out of this 100. So we can say that because the power is 80%, 80% of this total, that is 80, will be the reject null hypothesis and conclude the statistically significant results where of course the drug works in it, and the rest 20 it will be do not reject the null even though the drug works. These are actually false negative, as you know, while these are false positive. The power is basically a proportion of statistically significant result out of all the results where the drug works. Now alpha is something to do with false positive, as you know. So the false, how do you calculate that false positive? So here as the alpha is 0.05 or 5%, so 900's 5% is the proportion of the false positive. So 900 multiplied by 5 divided by 100 is equal to 45. So 45 is a false positive, while 900 minus 45 is equal to 855. This is don't reject the null when the drug is ineffective. This is absolutely fine. This is also absolutely fine, while this one is false positive, while this one is false negative. These two are erroneous columns here. Now coming to the final one, that is basically the FDR. FDR is this one. This particular column has to do with the FDR, false discovery rate. So FDR is nothing but proportion of false positive out of the total, right? So let us also write the totals below, because the total makes sense here in this calculation. So the total 45 plus 80 is 125. So now this one has to do with FDR. So now to calculate FDR, it's actually very simple, proportion of false positive out of the total. So 45 out of 125 is false positive. So is FDR. FDR is equal to 45 divided by 125. So that is equal to 36%. That is quite significant. 36% is that when the PP is 10%. So let us say here we can write when PP is 10%, it is basically 36% is the false discovery rate. So which is quite significant. If you have prior expectation 10, that is what you are going to get. Now let us see that this is the calculation for the PP is 10%. Now let us also calculate the same thing for a different PP. Let us say the PP is now is 80%. So instead of 10%, if it's 80%, what will be the result? So we will have to remove all these whatever we have written inside, because all these numbers will be different. Now let us consider yet another drug B. So in this case the prior probability is 80%. You know, so assume that the power is 80% and significance level is 0.05, just like in our earlier example. How much would be the FDR of this when the prior probability is 80%? So in this case, you know a lot about the pharmacokinetics of this drug and you really expect that the drug will work. So your expectation is very high. Then how much would be the false discovery rate in this case? Let us do the same calculations on the whiteboard. Okay, so if the power is 80%, that means out of 1000, 80% is it's not the power, I'm saying the posterior probability, right? Prior probability. If the prior probability is instead of 10%, if it is 80%, so out of 1000, the 80% of 1000 is 800. So for the 800 persons, this is going to be the drug will work, while the rest 200 the drug will not work. So it's very easy to fill this column. It depends only upon the prior probability or PP values. Now let us fill this column based upon the power. So power, as we know, it is 80%, while sigma is 0.05 or 5%. So just multiply with 0.05 in this case, or just multiply the value with 0.8 to get this power. So as you know, the power is 80%, so 80% of 800 is 640 is true positives, while the rest is 160 is false negative. So 200 multiplied by 0.05 you can simply calculate these values. So to this one, because this sigma is 0.05, false positive is going to be 10, because you are just multiplying 200 with the 0.05, 10, you are getting the false positive, while the true negatives are basically 190. Now you can calculate the total. Here the total is going to be 10 out of 650, right? This is 640 plus 10 is 650. So FDR will be, it is basically 10 upon 650. 10 out of 650 is the FDR, that is coming to be around 1.5 percentage. So 1.5 percentage is a false discovery rate, which is very, very low when our prior probability is 80 percentage, right? So let us say for 80 percentage, now let me erase the first row here. This also I'll delete. So if prior probability is 80 percentage, FDR is 1.5 percentage. See, if the prior probability is high, FDR is very low. If the prior probability is low, FDR is quite high. Now let us put, what if the prior probability is really low? Let us say 1 percentage only. So in that case, PP is 1 percentage. Then in that case, FDR is what? So to calculate, let us erase all these things, and then we will see it is actually a very simple calculation. Now let us consider drug C. So the drug C, the prior probability that, because you know nothing about the drug C is something like a random trial and error, and you don't expect anything. So your prior probability is just 1 percentage. Assume that the power is 80 percentage and significance level is 0.05. Now how much would that be, the false discovery rate? Let us do the calculations once again. Alright, out of 1000, if the power, if the PP is only 1%, so 1 percentage of 1000 is what? So it's just 10, while the rest is 990 will be drug is ineffective. So drug works, drug doesn't work in most of the cases. Drug works only in very less cases here. So out of 10, 80 percentage of 10 is basically 8, while the rest is 2. False negative is only 2 in this case. So out of 990, as the sigma is 5 percentage, multiplied to get the false positive. So the false positive is going to be 49.5, while the rest is 940.5. 940.5. And the total comes 57.5, while this total is 942.5. So this total makes no sense. You don't really need to calculate that as well. So this, now coming to the FDR is 49.5 upon 57.5. So that comes to be 86. So look at this, 86 is the FDR. FDR is equal to 86. That means very high chance of finding false positive. False discovery rate is very high. So the prior probability is only 1 percentage. The false discovery is extremely high, while prior probability is quite high. The FDR is only very low. So that is why the p value actually makes sense only in the light of the context or the prior probability. So prior probability is extremely important. Although to decide the prior probability is it's a Herculean task. False discovery rate, as we have seen, depends upon the context of the study. So there is a very famous statement by Stephen Jay Gould. He is the one of the founding fathers of the discipline of the evolutionary biology, the modern evolutionary biology, from the Harvard biology. So Harvard University in the US, Department of Paleontology. He passed away a decade ago. So Stephen Jay Gould's statement is that facts do not speak for themselves, they are need to be, analyzed in light of the theory. Facts needs to be read in light of the theory. So you have to consider it. Just by looking at an FDR or a p-value, you can never make conclusions. You have to look at the context of the study. So that is why FDR is very important comparing with the p-values. FDR depends on the context of the study or its prior probability. So if PP is not precisely, Bayesian inference explained in a later module makes sense. Otherwise, Bayesian inference as well as FDR are little more than just subjective feeling. FDRs are more accurate than your prior probability. So it's no more accurate. It's just same thing. So if you give a prior probability, the low, then probably you will get a low FDR. If you give a very high prior probability, then probably that FDR is also going to be high. So it's really depends upon your prior probability. So if your initial prior probability itself is erroneous, then FDR is also going to be erroneous. So in summary, statistical power is a fraction of the statistically significant results out of all results where the null hypothesis is false. Power depends on the sample size, variability, that is standard deviation, and choice of the hypothetical effect size. So you will get a very high power. So when you use large sample, looking for a large effect, or the data with little scatter, that is small standard deviation. Statistical power is important while deciding how many samples to use in an experiment. So that is why the calculating the sample size matters. So we are going to explain that in the next section. A power of 80% is commonly adapted, across the sciences. If the null hypothesis is false, then the beta is the chance of making wrong decision, that is called false negative. So false discovery rate or FDR is a fraction of false positives out of statistically significant results. So it quantifies false positives in your significant results. So where the p-value is less than 0.05. If prior probability is not precisely, then Bayesian inference makes sense. Otherwise, Bayesian inference and FDRs are little more than subjective feeling. Thank you so much.